Ever think about what happens to all that used cooking oil from restaurants and kitchens? A lot of it just becomes waste. But what if we could take that greasy problem and turn it into a high-tech, super efficient fuel? Well, today we're going to dig into a fantastic study that does exactly that.
See, it's one thing to just turn waste into something useful, but it's a whole other ballgame to get that process perfect, to squeeze out every single drop of potential. So let's dive in and see how scientists are figuring out the perfect recipe for a greener future.
All right, but before we get into the nitty-gritty, let's meet the mind behind this research, Dr. Mahmoud Karimi. His work is all about these key areas you see here, like waste valorization, which is just a fancy way of saying turning trash into treasure, and developing advanced biofuels. This study is really a perfect snapshot of his whole mission, creating smart, efficient tech for a circular economy.
So, here's what's on the menu for today. We're going to start with the basic challenge of making biofuel. Then, we'll explore a really powerful concept for measuring efficiency called exergy. After that, we'll look at the actual experiments to craft that perfect recipe, and finally, we'll wrap up with why all this really matters.
First things first, the big picture. We all know biodiesel is a fantastic alternative to fossil fuels, right? It's renewable, biodegradable, non-toxic, all the good stuff. But there's always a catch, isn't there? And in this case, it's the cost.
And yeah, this is the heart of the issue right here. A whopping 75% of the cost of making biodiesel comes from the raw materials, things like fresh vegetable oils. That's why using something cheap, like waste cooking oil, is a total game changer. It's what makes the whole idea economically viable.
Okay, so if we're going to make this work with waste, we have to be super efficient. And to do that, we need a better yardstick for measuring efficiency itself, something that goes way beyond our usual ideas about energy.
And that brings us to this really cool concept at the heart of the study, exergy. You know, we all learned in school that energy can't be created or destroyed. First law of thermodynamics, right? But the second law, that's where it gets interesting. It tells us that in any real-world process, some of that energy it becomes useless. Think waste heat. Exergy is the measure of the good stuff, the useful part of the energy that can actually get work done.
And this concept, right here, is the absolute key to true optimization. When you focus on exergy, you're not just counting the total energy in and the total energy out. Nope, you're looking at the quality of that energy.
So here's the official definition. But think of it like this. Exergy is the absolute maximum punch a substance can pack. And unlike energy, you can totally destroy exergy. Every little inefficiency, every bit of waste, that's exergy being destroyed.
And this gives the researchers a super clear target. A truly efficient process is one that destroys the least amount of exergy possible. By tracking where that exergy gets lost, they can pinpoint exactly where the system needs improvement. It's the tool they use to find that perfect recipe for biodiesel.
So how did they actually take this idea of exergy and use it in the lab? Okay, let's get into the experiment itself.
All right, so the whole thing basically happens in two big steps. First up, esterification. You can think of this as the cleanup crew, prepping the old, dirty cooking oil. Then comes the main event, transesterification. This is the big chemical reaction where they use methanol and a catalyst to turn that oil into actual biodiesel, or what scientists call FAME. And it's this second step where all the optimization magic happens.
So they zeroed in on three key things to get right. First one, the methanol to oil ratio. You obviously need enough methanol to get the reaction going, but does that mean more is always better?
Well, the results shout a loud nope. At a 4-to-1 ratio, the reaction just sputtered out. But at 12-to-1, way too much methanol actually started to mess things up, hurting efficiency and just creating more waste. The sweet spot, the absolute peak for exergy efficiency, was right there at an 8-to-1 molar ratio.
Okay, next on the list was the catalyst. In this case, potassium hydroxide, or KOH. A catalyst's job is to speed things up, but how much do you really need?
And wow, this chart is a perfect example of less is more. Peak efficiency, right at a 1% concentration. Any higher than that, and you actually kick off a nasty side reaction called saponification. Basically, you start making soap instead of fuel. And that, as you can imagine, totally tanks your yield and efficiency.
All right, the last piece of the puzzle they adjusted was temperature. You know, chemical reactions can be picky about heat. So what was the perfect temperature for this whole process?
And in this case, turning up the heat was a good thing. As they went from 45 up to 55 degrees Celsius, the efficiency just kept climbing, and the biodiesel yield skyrocketed from around 75% to over 90%. So 55 degrees Celsius was the winner.
So after all that careful tweaking and measuring, what's the big number? By putting together that perfect ratio, the perfect catalyst amount, and the perfect temperature, the researchers hit a maximum exergy efficiency of 91.7%. That is just an incredible number, especially for a process that starts with garbage. And there you have it, folks. The perfect recipe for turning old cooking oil into top-tier biodiesel. An 8-to-1 methanol to oil ratio, 1% catalyst, and you cook it all at 55 degrees Celsius. This is literally the blueprint for maximum efficiency.
Okay, so we've got the recipe. That's awesome. But let's zoom out for a second. What does this highly specific lab work really mean for the rest of us? Why does it matter so much? Oh, it's a huge deal, and here's why. First, you're literally upgrading waste. You're packing more useful energy, more exergy, into the final fuel. Second, by optimizing everything, you're also reducing waste during production. It's cleaner all around. This whole thing is a beautiful example of the circular economy in action, taking something nobody wants and turning into a high-value renewable fuel. But maybe the biggest lesson here is the method itself. This exergy analysis, it lets us go way beyond just asking how much stuff did we make. It lets us ask how perfectly did we make it.
And at the end of the day, this really isn't just about cooking oil, is it? What this research gives us is a powerful way of thinking, a framework we can apply to all sorts of other waste streams. It really leaves us with this big, exciting question. If we can get this close to perfection, turning fryer grease into fuel, what other junk that we throw out every single day is just waiting to be transformed?